Um, Good afternoon, my YouTube viewers. It's Crystal here. I'm just wanted to make you another video, and I'm going to make you another video on the Monte Carlo approximation. And so basically what it is Monte Carlo is associating with Bayesian statistics. And at the moment I'm studying Bayesian statistics. And so basically what they did was they did some Monte Carlo demonstration simulations or approximations in R, but I wasn't really happy with what they did in R, so I wasn't sure what to do. It's a little bit difficult to translate code from R to Python. So what I did, I had to ask my good friend Copilot to help me out. And so this is what Copilot has come up with, but it is a Monte Carlo approximation. And so we're going to do two approximations, one approximation on the beta distribution and another approximation on the gamma distribution. So the first thing that you want to do is you want to import the libraries that you're going to use. And so we're going to import NumPy to make numerical computations. We're going to import Matplotlib to visualize the data, and we're going to import SciPy to make the beta distribution. We're going to initialize our variables. So M is your Monte Carlo. We've initialized it to 100, but you can initialize it to 1,000 or 10,000 if you like. I've set A is 2 and B is 2. And A is alpha and B is beta. So now I'm going to generate M samples from the beta distribution. So we're going to have 100 samples from the beta distribution. So samples equals beta.rvs, A, B, size equals M, and RVS means it's randomly generated samples. We're going to plot a histogram of the samples that we have randomly generated. So plt.hist, samples, bins equals 20, density equals true, alpha equals 0.6, and color equals G for green. We're going to plot the beta distribution for comparison. So x equals np.linspace 0,1, 100. PDF equals beta.pdf xab. So PDF is probability distribution function. And plt.plot x PDF k line width equals 2. So we're going to plot the Monte Carlo distribution. We're going to plot our X label and our Y label, and we're going to show it. And we're going to calculate and print off some statistics. So we're going to print the mean and the variance. So this is the beta distribution that we have plotted with a 2 alpha and a 2 beta. And it also has a kernel density estimate on it. So you can see the beta distribution, which is what I wanted. So if you change the A and the B variables, then the beta distribution is going to change its shape. And so that's why I selected 2 and 2 to give you a nice similar to bell curve shape, the normal distribution, but you could have any distribution that you wanted if you changed it. So the mean is 0.497 and the variance is 0.0468. So now what we're going to do is we're going to do a Monte Carlo simulation with the gamma distribution. And the gamma distribution is what I have used in the course that I'm taking, and they did it in R. But as I said, I personally, it's very difficult to translate from R to Python, so I had to ask my good friend Copilot to help me. So again, we import our libraries of NumPy to make numerical computations, Matplotlib to plot the data, and SciPy.stats.gamma to create the gamma distribution. So we set up our parameters as m equals 100, but you can make it 1,000 or 10,000 or 100,000 if you like. And then A, that's your alpha, is 2, and B, that's your beta, is 1/3. And we're going to generate the samples. So samples equals gamma.rvs, brackets A, comma, scale equals B, size equals M. RVS means it's randomly generated sample. And we're going to plot it on a histogram. So plt.hist on the samples, we're going to have 20 bins. Density is true, alpha is 0.6, and color is B for blue. We're going to plot the gamma distribution for comparison. X equals np dot linspace 0, np dot max samples 100. PDF equals gamma dot PDF brackets X, A, scale equals B. And then so PDF means probability distribution function. And then we're going to plot the X PDF K and line width equals 2. And then we're going to plot our title, our X label, and our Y label, and we're going to show it. And we're going to calculate the mean and the variance. So, and now what we have is we have the gamma distribution with the kernel density estimate plotted on top, overlaying it. So you can see that your gamma distribution is right skewed. And the mean is 0.69 and the variance is 0.205. So this concludes our Monte Carlo simulation for the beta distribution and the gamma distribution, which is what I've been studied it in R, but originally I wanted to do it in Excel. I'm not sure if I can do it in Excel. I can ask my good friend Copilot if it can help me, but this is what we've got. So I think I've covered everything I wanted to cover. I've covered that Monte Carlo approximation is part of Bayesian statistics, and we've covered the beta distribution and the gamma distribution, and we gave you code examples on how to do that. So I'm going to conclude this video. If you like my video, please like and subscribe, and thank you very much for watching my video. I look forward to making another video for you in the very near future on a technical subject.